Today we want to look at more shortcuts to differentiation. The way that differentiation is set up is we get a bunch of base derivatives and then we learn some rules for when we have combinations of those base derivatives. We need to learn some derivatives of some base model functions, and then we learn things like the chain rule and the product rule and the quotient rule. And we just build more complicated functions by combining. So the structure is we get some base derivatives. And then we learn some derivative rules. We learn some base model derivatives, and then we learn some derivative rules. Right now, we only have one base derivative and one derivative rule, so life is pretty simple. But in the category of derivative rules, we have things like the chain rule, which is the derivative of a composition of functions, where we take the derivative of the outside function with respect to the inside function, and we multiply by the derivative of the inside. That's the one that we learned yesterday. In Leibniz notation, we might write df dg. The derivative of f with respect to g times the derivative of g with respect to x. Keep in mind, I didn't prove this rule. I just stated this rule. Proof by authority. Trust me, this is how it works. We do need to learn two other rules. Actually, we only need to learn one other rule, but we're going to learn two other rules. We're going to learn the product rule, which is for products of functions, and the quotient rule, which is for, wait for it, quotients of functions. Chain rule is the only one with the weird name. So the quotient rule would be for something like the derivative of f of x over g of x. And the product rule would be the derivative of f of x times g of x. So what we need, the base derivatives are the things that are going to show up in our derivative rules as f of x and g of x. The base derivatives are all of our choices for f of x and g of x. So here in the base derivative, this is all of our choices. For f of x and g of x in the derivative rule. So the base derivatives, I call them base derivatives. I didn't know what else to call them. These are all the choices of things that we're going to use, the ingredients that we put into the chain rule, product rule, quotient rule. I call this Taco Bell theory, because Taco Bell has about like 7 or 8 ingredients, and then they just put them together in various forms. That's why one of the greatest jobs in the world probably would be Taco Bell research and development. You've only got 7 ingredients. You don't have to invent anything new. You just put them in some new combination and then sell it to corporate. Right now, we only have one in the category of base derivatives. That's why our derivatives yesterday were pretty straightforward. We have nx to the n minus 1. I'm going to start writing these in with our Leibniz notation. Remember, if I just write d over dx, it's like d blank over dx. This says take the derivative with respect to x of whatever I write next. So the derivative of x to the n is nx to the n minus 1. And we got a lot of mileage out of this. The derivative of x to the n is nx to the n minus 1. We want to add to this list. So the other things that we're going to want here are exponential functions, logarithmic functions, trigonometric functions, inverse trigonometric functions. That'll carry us quite a long way. So the other things that we want to add to this are exponential functions, and logarithmic, trig functions, and inverse trig functions. I'm going to put and many more. These first three categories will get us a long way. We've got algebraic functions, and we've got our most important transcendental functions. I feel like I'm forgetting something, but it'll come up later. That's why the question mark. There's also the hyperbolic functions, which is really kind of weird to include because it's not like we've spent a lot of time doing hyperbolic geometry. How much time did you spend in your geometry class rewriting the parallel postulates? How much? How much? None. No one ever has. And yet we still like all hyperbolic functions. I don't know why. Hey, things are weird. Math is weird. It's because we can take the derivative. Derivative of hyperbolic cosine is hyperbolic sine. Everybody's like, oh, that's easy. Let's include that. It's like, oh, they don't know hyperbolic geometry. If you showed them a triangle with 3 right angles in it, they would not be happy. Let's do it anyway. So the way that this works is that we learn one of the base derivatives, and then we start combining it with other stuff, what we already know. So for example, I like to do trig functions first. The derivative of sine is cosine. That's how we'll say it. We'll say it without the of x parts. The derivative of sine of x is cosine of x. Specifically, the derivative with respect to x of sine of x is cosine of x. See, as soon as you start trying to include all the words, it just becomes excessive. So we're just going to say the derivative of sine is cosine. And today it's going to be especially annoying because you're going to hear me say the derivative of sine is cosine a lot of times because songs don't get stuck in your head because you hear them once. You hear them over and over again in a short amount of time, and then you can't get them out of your head. So the derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of sine is cosine. The derivative of cosine is negative sine. You're going to want to remember which one gets the negative. Derivative of cosine is negative sine. The derivative of sine is cosine. One way that we can help ourselves remember this is to imagine the graph of the sine and the graph of cosine, and remember what the derivative is supposed to be telling us. So let's draw a quick picture of a sinusoidal function that we can use for sine or cosine. Remember, when you're drawing a sinusoidal graph, you need to separate out into threes. So we're also going to have a quick review of how to draw a nice-ish sinusoidal graph. But vertically, we need a middle, we need a top, and then we need halfway. We need a bottom, and then halfway. So I need a middle. I need the top. And then I need a bottom. And then I need the halfway of each of those. So I need a middle. I need a top. I need the bottom. And then I need halfway. Horizontally, we need 3. We're going to take one circle, and instead of breaking it, and we're going to break it into quadrants, and then each quadrant is going to have 3 parts. If we're thinking in terms of degrees, we're going to mark every 30 degrees, although we're not going to label it, gets too crowded, but we need 3s. So if we're going to start here, I think that's where I intended to start. We're going to separate it out in 1, 2, 3. There's the first quadrant. 4, 5, 6. There's a second quadrant. 1, 2, 3, 4, 5, 6, 7, 7, 8, 9 is the third quadrant. 10, 11, 12 is the fourth quadrant. 3s, 3s. 30, 60, 90. 120, 150, 180. Don't worry about the 45s. Those are hard to locate anyway. We're going to throw a few extra quadrants on. And we're going to start by drawing the sine. Sine starts off at the middle and goes up. Sine starts off at the middle going up. Sine of 30 is a half. We're going to hit the halfway points, 30 degrees off of the middle. So sine starts off at the middle. Sine of 90 is 1. Sine of 180 is back to 0. Sine of 270 is down to -1. Sine of 360 is back to 0. Sine of 90 after 360, 450, doesn't matter. 90 after 360 is back at the top, 1. And then sine of 450 plus 90 will be back at the middle. I don't know my full and half rotations. You can tell I'm not a fan of extreme sports. This is what sine does. Starts at the middle going up, then hit top, middle going down, bottom, middle going up, top, middle going down, bottom. So we don't just want to draw a jagged zigzag line. We have better resolution than that these days. Here's how we do it. We find the halfway points. Remember, this is marked at 30, 60, 90. 1/3 of the way is where we hit a half. That's what we want to remember. We can just remember sine of 30 is a half. 1/3 of the way is where we hit a half. So 1/3 off the middle is where we get to a half. 1/3 off the middle is where we get to a half. 1/3 off the middle is where we get to a half. 1/3 off the middle is where we get to a half. 1/3 off the middle is, that's not a middle. A third off the middle is where we get to a half. Here's the middle. A third off the middle is where we get to a half. Here's the next middle. A third off the middle is where we get to a half. And now we're starting to get a little bit better bend in our graph. We don't just want to draw a straight line up to make a corner. We know this function is differentiable everywhere, so we need to figure out how to round it off. 1/3 from the middle on either side is where we get to a half, because sine of 30 is a half. Next thing we want to do to draw improve our sinusoidal graph drawings. We know that at the top and the bottom, the function is turning around, the function goes flat. So I'm just going to draw a little flat at the top. Not big, just a little to remind myself that I got to come in flat at the top and the bottom. Next, connect the halfway points through the middle. Connect the halfway points through the middle. Just connect them with lines. They're not lines. We're drawing a sketch. They're line enough. Connect the halfway points through the middle with lines. They're not lines, but for a sketch, that'll do. Now, we just have to connect the angle that we're coming off those linear sections and flatten them out to make a nice sinusoid. So I usually start off at the flat part and I come out flat and then just kind of match. So it connects smoothly. Remember, we're trying to draw something that's differentiable, and we know that differentiable means the slopes line up. So the slope coming out the top should match up with the slope coming out the middle. That's what we're trying to go for. We don't want like a corner show up there. So I come out flat and try to match the angle. And then at the bottom, come out flat, match the angle. I have trouble drawing the other two from that angle. So we're going to come out flat, match the angle. Come out flat, match the angle. Come out flat, match the angle. If you're wondering, the way changing my complete orientation does not change how I have to move my hand to draw it. It doesn't. It does in my mind, though, and that's all that matters. I don't know why it works that way. I can't draw the other ones from this side of the table. I have to stand on that side of the table. Any questions? So this is how we can get reasonable graphs of sinusoids. What we want to know is, what we want to remember is that sine of 0 is 0. So sine starts here, goes up and then down and then up again. See, I've made it a little fat over here. Oh well. Remember that cosine starts at the top. I didn't label these down at the bottom because sine and cosine have different starting points, right? So cosine starts up here at the top. So if I want to take this, I could just shift it all over, or I could just draw the cosine starting up here. So our cosine start is up at the top. Our sine starts in the middle. All this was in service of remembering which one of these throws the negative. The derivative of sine is cosine. Derivative tells us slope of the tangent line. If we look at the slope of the tangent line at 0 for sine, it's positive. So derivative of sine is cosine, because sine starts off going up at 0. The derivative of cosine is negative sine because cosine starts at the top. So cosine starts off going down. So we have negative slope coming off the cosine. It's 0 at the top, but then it just immediately goes negative. That's that silent moment on the roller coaster before everybody starts screaming because the thing is falling. Remember that sine starts in the middle heading up, and that tells you positive. But cosine starts at the top. So this means we can retain our default settings that up is positive and down is negative. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of sine is cosine, positive cosine. The derivative of cosine is negative sine. You can't see it on the video. I'm doing hand signals. The derivative of sine is cosine, positive cosine. The derivative of cosine is negative sine. Now, if people are watching at home, they're like, "Oh, the hand signals didn't help." I know they don't help the audience, they help me. It's me that I'm worried about. So we have to be able to combine this. We have to take these two things. You have to remember these things. You don't have to memorize these things, you just have to remember them. If that means that you have to sit down and memorize them, that's a you problem. You just have to remember these things. Does everybody know the difference between remembering and memorizing? You didn't memorize the words to your favorite song. You just remember the words to your favorite song because you've heard it a bunch of times. Memorizing would be like sitting there listening to a section, trying to sing along with it, rewinding it to make sure you got it right. That would be like memorizing, where you're actively trying to remember. If you just sing along with the song and then eventually figure out what they're saying, that's just remembering. I remember Paul Revere. I memorized Yakko's World. Those are references older than everybody, almost everybody in the room. So now that we have a different style of function, we could start using this with our one rule that we know, which is the chain rule. So for example, I can make a function. Remember, I have a few things that I could use for my f of x and my g of x. And so I'm still going to be naming things y, because we're still might be using the language of f of x and g of x. It might not be automatic for us yet, so I'm just calling it the functions y. And I might say something like sine of x squared. We have a composition of functions. We have to think about what happened in this function. If we look at what happens to x and follow the path of things that happen to x, first the x gets squared. Second, we do the sine of the result. That tells us what the inside function is. The first thing what happens to x is x squared. So that's our inside function. In the notation that we used yesterday, that's the g of x. So here the inside or the g of x, is x squared. The outside function is sine. So it's sine of stuff is the way we're reading this. It's the way that I'm reading this, and I have bad habits. Maybe you shouldn't be copying that. But I would refer to the sine as the outside. I'd say the outside is the sine, which is the f of x in our notation that we established yesterday. Although I just called it f of stuff, is sine of stuff. So if I want the derivative of sine of x squared, it's cosine of x squared times the derivative of x squared. So y prime, the derivative of sine of stuff is cosine of stuff times the derivative of the stuff. The inside was an x squared, so the derivative of sine of stuff of x squared is cosine of x squared times the derivative of x squared, which is 2x, times the derivative of x, which is 1. And that's where we stop. This is not how we should write this. It's really sloppy to write your polynomials at the end of your trig functions. So I want you to look at this. I don't know if you see this as being poorly written, but I want you to look at this and start thinking this is poorly written. I'm trying to speed run you not liking this notation style, where you write the polynomial afterwards. Your polynomial should be your coefficient, right? This is how you build prejudice in students. You say, ew, that's a terrible way to write it. And students are like, oh, really? I don't see anything wrong with it. It's like, oh, no, you see something wrong with it. You're like, all right, I see something wrong with it. And then, 20 years later, it's like, well, why was that wrong? It's because your teacher was an asshole. And you look back, it's like, well, I'm dead now, so ha! So this is, I don't like this. I'll just phrase it that way. I like my polynomials to go in front of my trig functions. And I'll say this is a better way to write it. So I'm going to say it's better to put your polynomial factors first, and then I'm going to put better in quotes because, I mean, it doesn't really matter. But if you want to fit in, you're going to write your polynomials first. If you write your polynomials at the end, people are going to be, oh, you write your polynomials after your trig functions? Oh my gosh. They won't say that to you. They'll be saying it behind your back. Academics are catty, what can I say? Notice that I can take these two functions and I can have them apply in the other order. Compositional function is not commutative. So if I apply them in the other order, then it's written different. And we might say, as another example, y is equal to sine squared of x. This is read differently. Here I've switched the inside and outside functions. Remember when we write sine squared of x, we mean sine of the square of the sine of x. So by this, we mean sine of x squared. So when we read inside outside on this function, inside is sine, outside is square. So our g of x is sine of x, and our outside function or f of stuff is stuff squared. So our derivative is that we're going to use the chain rule because we have a composition. We've identified inside, outside. We're making a composition, y prime. The derivative of the outside with respect to the inside. The derivative of something squared is 2 times that thing to the first times the derivative of that thing. That thing in this case is the inside, which is sine of x. And the derivative of sine of x is cosine of x. This would be an excessive amount of stuff to write, but this is what's happening when we think about the derivative of sine squared x. It's good to build habits when you're writing, especially. Actually, even more especially when you're typing. It's good to build the habit of writing parentheses around your argument, especially if you're going to be stacking trig functions with other things. Because we want sine of x. We want to make sure that x shows up in parentheses. We want to make sure that we close the parentheses around the first x so that it's separate from cosine of x. Any other way I could write sine 2 sine x cosine x? Anybody recognize this? This would be a really difficult thing to recognize. I'm going to give a hint. Hey Siri, what are the double angle identities? Oh, she just looks them up on the internet too. Thank you, Siri. Oh, and then she turned off. The most important thing about all those trig identities that you were forced to remember is remember what categories there were and what they were called. Remember that there was a thing. So this 2 sine x cosine x, I could rewrite that as sine of 2x. If you want to show off your mad trigonometry skills. That would be a dangerous thing to do if you're writing stuff down and handing it to me to grade. Because remember, I grade very quickly and I would just see the sign and I would just kind of like gloss over. It's like, oh, you forgot the 2 in the cosine. And you'd be like, oh, I put the 2 in with the x. And I'd be like, oh, ah, shit. And then you'd have to bring it up here. Then I have to fix it and I have to go in the grade book and do it. It'd be a risky thing to do. But if you want to flex your mad trigonometry skills, remember your double angle identity. Any questions? Derivative of sine is cosine. Derivative of cosine is negative sine. You got to remember those 2 things. You got to remember which one gets the negative. The graph might help you do that. Or you just got to memorize stuff. But wait, there's more in the category of trigonometric functions. The derivative of tangent is secant squared. And the derivative of secant is secant tangent. We can also write similar derivatives for cotangent and cosecant, but these are the 2 that we're going to care about. These are the 2 that won the franchise wars. And so when we need functions that under differentiation go from degree 1 to degree 2, these are the 2 that we'll focus on. Plus, I mean, it's all set up. So like, we make tangents out of secants and stuff. So it fits with the theme. One of the things that's weird about these is that we go from degree 1 trig function, differentiate into a degree 2 trig function. That's a little bit weird. But tangent and secant are a little bit weird because they are not continuous everywhere. Remember, tangents and secants have all those vertical asymptotes all over the place. So that accounts for some of the weirdness. That's a very hand-wavy account of some of the weirdness. But you need to remember that these are weird, that when we differentiate, they go up in degree. Just as a reminder, this is like tangent to the first. So it's like we go from degree 1 up to degree 2. This is secant of the first, tangent of the first, but that's degree 1. Here's 2 degree 1s in a product, so that's degree 2. We don't have the quotient rule yet, so I don't have a nice graph way to go about this. So start off, just remember the derivative of tangent is secant squared. The derivative of secant is secant tangent. So if, for example, I wanted to find, if I set y up as secant of x cubed, the inside is x cubed, the outside is secant. We're taking the derivative of secant of stuff. Our breakdown from before, inside, or our g, is x cubed, outside, or the f is secant. So our derivative, y prime, the derivative of secant of stuff is secant stuff, tangent stuff. So it's going to be secant tangent times the derivative of the stuff. The derivative of secant x cubed is secant x cubed, tangent x cubed, times the derivative of x cubed, times the derivative of x, which is 1. This is weird because the derivative has x showing up twice. This, once again, we're writing our polynomial at the end, and there's polynomials inside of our trig functions. Messy. If you're fighting with Canvas and you type this with the 3x squared at the end and it marks you wrong, it's probably just, I forgot, it didn't even occur to me to put that one. And I automatically moved the 3x squared to the front. So try just moving the 3x squared to the front. Questions, comments, snide remarks. 4 new base derivatives that we have to be able to incorporate with all of our others. From here, it's just a matter of practice. There's nothing magical that has to happen. This is just learning math is not about magic. It's not about skill. It's not about talent. It's about time. Learning math is a function of time. Learning math is a function of time. All that math cares about is that you spend time on doing math. The The only way to get better at this is to read some weirdo functions. You can tell the functions are getting weird for you when you start saying, when am I ever going to need this stupid function? As soon as you start to think to yourself, why do I need to know about this stupid function? That's when you know you're finally starting to be challenged. You're finally starting to do work. If you do problems in this class and you're not asking yourself, what the fuck is this for? You're not actually being challenged yet. It's not hard for you. So your brain is not trying to fight you, right? As soon as you start thinking, why do I have to know the stupid square root of tangent x? That's stupid. Once you start thinking that, that's your brain saying, this is hard and I don't want to do it. That's what that comes from. You don't actually care where this comes from. I could have a very legitimate reason for talking about the square root of tangent x. I don't have it. Why would I? I'm a math guy. I could have a very legitimate reason why square root of tangent x is super important to your future career as a fill in the blank. But the reason that you're asking the question is not because you care about that. The reason that you ask that question, specifically in math classes, is that shit just got real. You just started having to work. It's getting difficult and you don't want to do it. That's why you're trying to come up with reasons to not do it. Does that make sense? You really need to understand this. You really need to understand that when you start fighting against the material and trying to diminish the material, it's because you don't want to cope with it. It's because you don't want to do the work that's going to be required. And you're saying, nope, I'm hitting the eject button. And then you want to take that realization and see how far it spreads through other aspects of your life when you want to bail. Does that make sense? Sometimes bailing is the legitimate answer. Just want to put that out there. But think, am I trying to avoid this because it's difficult and I don't want to do it? Or are there actual reasons why I should watch the rest of the movie instead of go downstairs and change the laundry out? I don't know. I'm just trying to pick up some random chore. You know what I mean? Always think about that. If that sounds exhausting, fuck, it is. But you sign up for college, you try to banish ignorance. Ignorance is bliss. Knowledge is a pain in the ass. So you sign up for it. So if you're going to be more, if you think all this knowledge is going to make me miserable, yes, it is. So be happy about that. You know what I mean? We're going to read this as an inside is the tangent x and the outside is square root of x. Because this is a vital function in your future career as a blank engineer. I've seen it happen. And I'm not lying to you right now. That's the Jedi mind trick way. Totally true. Sorry, this is a reading exercise. And I want to remind you that a square root is a 1/2 power. And we want to read this function as the tangent of x is being raised to the 1/2 power. And then we want to use our mad chain rule skills that we've been working on for almost 24 hours now and say that the inside function, our g, is tangent x. And our outside function, our f, is stuff to the 1/2 power. The reason I'm writing stuff to the 1/2 powers is this is one of our favorites. It's an nx to the n minus 1. So our y prime the derivative of something to the 1/2 is 1/2 of that thing to the negative 1/2 times the derivative of that thing. That thing in this case is a tangent x. So the derivative of square root of tangent x is 1/2 tangent x to the negative 1/2 times the derivative of tangent, which is secant squared. This would look different if we had something different inside the square root, but we would still read the outside the same. So if, for example, I had y is equal to the square root of cosine x, I've changed the inside function, but my outside function is still the same. So y prime, the derivative of the square root of something is 1/2 that thing to the negative 1/2 times the derivative of that thing. That thing is cosine x. The derivative of cosine is negative sine x. This is where things are most dangerous. I'm multiplying by negative sine x, but I've written it as subtract the sine x. When we're multiplying, put in parentheses. Now, this is just raw data that we're spitting out running the program on the function. We would want to clean this up. We can clean this one up by saying, I'm going to put this negative 1/2 in the denominator. I mean, if we really want to be nice and clean about it. The problem was spoken to us in radicals, so we should speak radicals back to it. Here I've got a 1/2 and a negative. So, but these are all being multiplied together, so I'll make the whole fraction negative. In the bottom, I have 2 square roots of cosine x. And the derivative of cosine is negative sine. Any questions? These are handwritten versions of these. Single line syntax on this. That would be messy. Good news is we have lots of options for writing this in single line syntax. The bad news is we have lots of options for writing this in single line syntax. With that in mind, the other things that we're going to run along this week with learning our more rules, shortcuts for derivatives, is we're going to learn how to type things in Canvas. So we don't have to type them in single line syntax all the time. All right. That's it for today. You have 4 new base model derivatives to memorize. You have some chain rule to think about while you're doing so. That's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.